So what we're going to start today's discussion. We only have an hour and a half. Hopefully we'll be able to finish chapter 5 on the discussion of bipolar junction transistors, single-stage amplifier based on bipolar junction transistors. So we still have 2 more stages to go. I didn't have much time to go through examples, so I encourage you to do more exercise on your own, to follow through examples in the textbook or exercise in the back of the chapter, okay? So what we're going to do is, as I said, there's 2 more stages to go. So we're going to first introduce what we call the common base stage. And if you look at the structure, we already talked about, the stage we already talked about is that if you input in from gate, from base, output from collector, this would then give you a common emitter stage. But what if we change our input terminal and other than coming in from the base, you change your input. Collector is still the output, but we change our input. Instead of coming in from base, the input is connected to the emitter. This type of structure is called the common base structure because my base is the base terminal where I label it here, meaning that this is the common node, where the other nodes is where your signal is being carried through. So signal coming in, signal going out at these 2 other terminals rather than the common reference terminal. So that's called the common base. Of course, we're going to also talk about emitter follower. So emitter follower is the common collector structure where the signal coming in from base and signal out is at emitter terminal. That's called the emitter follower. So we're going to talk about these 2 structures. If you think about it, so we're going to start with the common base. The reason why we want to have another structure other than putting a signal coming in from base is basically we're seeking other features than providing a voltage gain. We already established that if you have the most common gain stage we talked about is the common emitter stage, which already provides significant voltage gain and its performance is relatively good. But so what if in some sort of a scenario you will then need to have, because in most cases, if you're dealing with voltage as your signal, you want high input impedance in order to take in the voltage, in order to make sure that voltage is coming into your VBE, which is the amplification, the amplification terminal. What happened is that if your signal, why do we want the first question is why do we want to change our architecture for establishing something called a common base structure? One of the key important aspects of the application is that if you're dealing with current amplifier, what happens if my input signal, is instead of having a voltage, you have an input which is a current, input current. So if my input signal is current, then I would then rather than having a high input resistance, I would actually prefer to have a low input resistance. This is where common base would come in. Well, the reason why is that we can use this 2-pole model for a current amplifier. If you're dealing with current as your signal source, then your input is current. So the source can be modeled as a Norton equivalent current source. So let's say this is my input. Instead of having input as voltage, my input is a current source. So the red part is actually a current source model with Norton equivalent model. And then you also want to deliver your signal out into a load. So if this is the case, this is the same as the analogy we talked about with voltage amplifier 2-pole model. This is just dealing with current. So input is current here, and your output current is actually here. Is whatever current is flowing out at the out terminal. If this is the equivalent circuit, I could quickly write down the corresponding output current and input current ratio. If you look at that, this would then depend on based on this current, it's a current divider. Therefore, your output current is this current. Let me just write down. So this is the input current. Output current is R out plus R load. R out. Ratio AIS I1. And we use this branch to establish the relationship between I1 and IN, so that I'm getting in this case, I will then get my I out versus I in will then become, let me just write down the results, IS plus I in IS times AIS times I out I load I out. Okay? So this is just a current dividing results. Your current ratio, this is called the real current gain, signal gain. Because my signal now becomes current, therefore it's current gain. Current output current versus input current. How much current gain can I obtain by using by this current amplifier? So you basically want to maximize this. So if you look at this, this is the same thing you look for, because these are parameters based on your setting environment. But these are the parameters we can design, 3 parameters we can design. So if you look at this, you want input, if you want to maximize this, how does one maximize? How to maximize current gain. Let's say this is my current gain. How does one maximize your current gain? Is to make input resistance, what? You want to make this as low as possible, right? So you want this to approach 0. We want the output resistance to approach infinite. So you get ideal current source. That's basically what it is. So to create a good current buffer, gain is not necessarily the most important thing. What you actually want is that it's independent of your source condition and loading condition. So if RL is infinite, which means that it doesn't really matter what my loading resistance is, it will always deliver the 100% of my current. And it will be independent of what my source resistance is. It will then take in all the current that's generated by the source. So you want it to be this would then become independent. So your results, I should say independent. So what we basically want, this would then give us a very powerful result, which is I out, your output current, become independent of RS. This is what we call robustness of your design. You want to design a circuit, design a house, which is independent whether the outside temperature is. It will always be 25 degrees inside. That's a robust design of insulation or whatever. So this is the same thing. You want it to be independent of your source resistance and loading. We call this loading effect or source effect. You want to be independent of that. So that's why we want to have low input resistance. That is why we have common base stage. Another key important application, this is more like if I could simply have a current buffer, meaning that I could simply have AIS equals to 1. That's also fine, as long as I'm transferring my current successfully from the input state, from the source, out into the next stage for whatever operation there is. The second, so as I said, one is for current amplifier or current buffer. So CB stage you typically use first is for current amplifier. If you're doing current amplification, then this is for amplification. It can also be a buffer. Buffer simply means that my AIS is 1. I don't necessarily need to amplify it, but just deliver it from, it's like an interfacing stage, dealing with current. The second application of a common base is what we call impedance matching. This is very, very commonly used in your in RF circuits, where you want to make sure that whatever signal coming in from the antenna matches whatever input stage, the input resistance. So this is simply to set your R in equals to R, for example, antenna. This is a particular setting to taking power that is depending on your input source. This is typically the resistance. Your typical resistance of an antenna. Okay, so if you have an antenna, something like this, its resistance, our antenna, typical number of an antenna is 50 ohm. So what we want to do is to make sure my input resistance is the same as the antenna resistance. That's called the matching. You want it to be identical in order to take in the maximum power. You can actually do the exercise on your own, but I'm just saying that you want to make sure that it matches so that it will maximize. I don't actually have time to go through the exercise, but delivered to circuit. So if your antenna is connected to a circuit, this is called typically an input stage. In this case, then you want to use a common base stage, because that would allow us to change my input resistance to a low level, which will match this, adjust my level to match the antenna resistance to taking the maximum power, okay, for the circuit to operate. So whatever signal that you receive from the station that's coming into your antenna needs to be amplified by the input stage. In this input stage, we need to have an input resistance which matches the antenna. And this is typically relatively low, and you could actually adjust. One of the key points is that the common base stage, one thing is that it has, its feature is that it has low input resistance, and you can actually adjust that to a level which meet this. So let me write it down. So the key feature for a common base stage, it has two features. Typically has low Rin. And then the second thing is that it's adjustable. It's relatively low, and it could adjust. Therefore, it meets these two requirements. Either you're dealing with input signal as current, or you want to take in maximum power from the antenna. Then you want to adjust it so that it matches. Okay. So let's take a look at how does one analyze a common base structure. So for a common base stage, we're going to go through the most basic structure is to assume RO equals to 0, equals to infinite, sorry. Ignore the effect of RO, then we're going to also look at, and we ignore the source resistance at first. So this is the case when I study the primary behavior of a common base stage. So for a common base stage, if this is the case, let me redraw it. This would be my circuit. if you're looking at a DC composition, this is my circuit. So this would then be the input terminal. This would then be the output terminal. So before we actually go into the analysis of finding out the key parameters as input resistance, voltage gain, output resistance, even though I'm saying that it's very similar to a current buffer, but we're still going to treat it as a voltage amplifier first. So what we want to do is to make this equivalent to this, again, a voltage amplifier first. So I want you to find the three key parameters. AVO, R out, R in. We still want to find these three key parameters. Okay? So how does one arrive at, to find these three parameters, we want to draw a small signal. Equivalent circuit. So how does it look like? We have, if you look at this, you have the base. So first, if you're not very familiar of how to construct the model, first I would suggest that you simply draw the small signal equivalent model of the transistor first. So this is the BJT. I have R pi, GM, V pi. This is V pi. Okay? So I'm ignoring RO because I'm assuming RO is infinite, so you just ignore that at the beginning. So then find out where my inputs are. The input terminal is here. This is the input terminal. And the output terminal is here. And at the output terminal, externally, what we have is this is common base, therefore, it's AC ground. And my collector terminal is connected to a RC and then connected to ground. This is another AC ground. So you have two AC ground. This is VB. This is VCC. Both AC ground. So then I'm assuming my signal is coming in from here. Right? This is my input signal. I'm going to look at how the circuit behaves. Okay? So if this is the case, let's write down the equation. We already assumed these. So we look at how does one find out, first of all, what is the output in terms of as a function of input. So your V out, if I'm writing down V out, is simply there's only one branch of current, therefore it's minus GM V pi times RC. Current times resistance give you the output resistance, output voltage. And my input voltage here will then equals to, if you look at this, my input voltage is actually this. Let me write down. If I'm writing down this loop will be V pi plus V in equals to 0. Okay? So then I know that V pi equals to minus V in. Therefore, you simply insert that back. My V out will be GM RC V in. Therefore, the voltage gain will be V out. By definition, V out versus V in when output current is 0, which is GMRC. Okay? So it could also still serve as a voltage amplifier, but one of the key important things is that the minus sign and this minus sign cancel each other. Therefore, you get a what we call the non-inverting it's a non-inverting amplification rather than inverting by 180 degree for common emitter stage. Common base stage means that the signal goes in the same direction, which means that if this is my input signal, V in, my output signal goes in the same direction. It's very important to know that it's a non-inverting amplifier. Okay? So if I show you this, like in a single choice question, you should be able to know that its common base would be able to deliver this. Common emitter will not because it will be inverting, right? The next thing, of course, so we already get one down. We already know voltage gain. We know that it's GMRC. And we're going to look at, the next thing is, of course, this is first one. We're going to look at input and output resistance. As I said, input resistance is the key factors when one designs a common base stage. We want to make sure that a common base stage will then have a low input resistance or adjustable. You want to make sure that you can design it. So that's very important. Let's look at its input resistance. So we're going to also draw our small signal equivalent model. So when we do this, this is the exact let me redraw it here. So when we test this, you simply insert a test current, test voltage, and observe its test current. I'm going to simply draw this equivalent circuit again. Okay? So you simply want to define R in. My definition is Vx, Ix. What? V pi. Oh, sorry. V. Thank you. So V pi equals to minus, that's why. There's a minus sign coming from this equation. Thank you. Okay? So let's go back and look at what the input resistance a common base stage will give us. So if you look at this, once again, we know Vx equals minus V pi. In this case, if you look at this loop, this is V pi. Okay? And what is Ix? Ix will then become, the current coming down is GmV pi. The minus sign is because current is going in. So there's a minus sign from current coming down. So these two branches would then give us Ix. So there will be minus V pi R pi. Okay, current coming from collector is Gm V pi. Current coming from base is V pi R pi. Two branches of current. Therefore, after some exercise, you simply substitute this into, so Ix will then become Gm Vx plus R pi Vx. This minus Vx in. So by definition, my Rin will then become 1 Gm R pi. So if you rewrite this equation, it will be simply 1 over Gm plus R pi. This will simply be R pi in parallel 1 over Gm. But because in most cases I have beta larger than 1. So in most cases, beta larger than 1, that is to say, your input resistance is simply approximately, okay? So this is one of the key equation you should remember for a common base stage. This simply implies that my input resistance, remember GM, this equals to ICQ So what does this imply? This simply implies that if I want to, as I said, if I want to do impedance matching, I could simply design my biasing point. And so that I could place it exactly to where I want it. So this is one of the key things. You want it to be a parameter which will then allow you to place it to a particular level so that it will meet your target. Okay? So this is one of the important things. We're going to talk about the design problem later. But that's very important to know that you will then have, let me write down here. So we already arrived. This second is that we know that my input resistance is 1 over GM. And we still have one blank spot to fill, which is output resistance. So going back to this equivalent circuit, you could actually get the output resistance fairly quickly because you still have, if I'm looking in from here, so if I'm not going to redraw this, if I'm looking in from here, the same thing happens is that if I'm looking in from here, if you ignoring the effect of output resistance, RO, of the transistor, early effect, this will then give me infinite resistance. Therefore, you only see RC. So you don't actually need to do anything. Just simply looking at the equivalent circuit will simply tell us that my output resistance is RC. Okay, so this is when, remember when we're ignoring early effect, and then we're assuming that there's no source resistance effect. Okay, good. So the next thing we're going to do is to look at what if I bring them in, these more complicated version. So with source resistance, what happened is that anytime you have source resistance, I can either use this model to add a source of resistance, or I can simply use this to add a source of resistance. It should give you equivalent results because it does not include the impact of output resistance yet. So let's see the impact of. The reason why we have to discuss this is because this is a low impedance amplifier. Therefore, any source resistance will then divide out the impact of your gain. So let's do it this way. So let's say input signal, your input is coming in here, R pi, this will be common. So if this is the case, what happened is that if you look at the output terminal, it's still the same. So the output terminal is still V out here. so GM V pi RC. This equation still holds. It's the same equation. The only difference is then you need to account for this voltage drop across RS when we figure out the relationship between V pi and Vn. So we're going to do the same equation, V pi plus the current coming down. The current coming down is V pi R pi plus GM V pi plus RS. So this is the voltage across resistance, source of resistance. Is being given by the current coming down and across this resistance. And then plus Vn. Okay? So if you look at this, this will then give you a different relationship between input and V pi. So then this equation will be 1 plus R pi GM RS. Right? So I'm simply taking out all the V pi component and insert it back. So then this V out, in terms of V in, so V in will be a minus sign 1 plus R pi RS GM RS over 1 V pi. Okay? Right? Did I get it right? Did I make a mistake? This is V pi. I wanted V pi in terms of Vn. I want to rewrite it as V pi in terms of Vn and then insert this back into this equation. Okay? So we get V out, V in. Let me just write down the equation. It will be 1 plus R pi RS GMRS GMRC. Okay? Did I get it right? I hope I'm getting it right. Okay, you simply insert this the whole term back into this equation, then we should be able to get that as our refined gain. So considering RS, this will attenuate the gain by a factor of almost 1 over GMRS. In most cases, we know that the source of resistance is typically not a very high level. If this is very high, then we will never use a common base stage. So just a little resistance source of resistance at the source. But in most cases, RS is smaller than R pi. So this equation can be revised as your voltage gain will then be GMRC 1 plus GMRS. So you actually see the degenerative effect 1 plus GMRS. Anytime we have a resistance connected to the emitter terminal, this is the same as GMRE. So you have this attenuation effect in the overall gain, voltage gain. Okay? This is simply voltage dividing because not all of the signals going into modulation, some of them will be dropped on the resistance. And because common base stage is not an ideal voltage amplifier, therefore, if you have some source resistance at your source, then this will lead to some attenuation of your amplification. Okay? The impact of source resistance will come in other than affecting the voltage, it will also affect output resistance in a sense that the same as when we talk about emitter degeneration. So let's think about it. So if I'm wanting to talk about R out of a common base stage with finite RS, with RS does not equals to 0. The previous case, we assume that RS equals to 0. We assume that RS does not equals to 0 and RO is finite. So if you have an output resistance, if you want to consider the effect of RS, it will only come in when you consider our output resistance. So we need to reconstruct our equivalent circuit. So if you want to look at this condition, this is common base, R pi. As I said, if you're not considering RO, you're assuming RO is infinite, then it will always be RC. You don't need to consider that. But if this RO becomes finite, let's see how that impacts our output resistance. So this is where we're looking at the output resistance. But typically what we do is that we bring into RO prompt. This is R out. So your output resistance of the stage will be RC in parallel RO prompt when we're looking at the collector itself, right? So let's find out what RO prompt is. If you look at this equivalent circuit, if I'm doing the testing, it will simply be Vx, Ix, right? So if you do this exercise, I don't need to go through this again because this is identical to the analysis we did on common emitter degeneration. Instead of having an RE, we have an RS. So this is the equivalent circuit. It's an identical equivalent circuit. Therefore, you could simply use that to find out your RO prompt. It will be RO 1 plus GM R pi in parallel RS. Instead of RE, this becomes RS. So it will have an identical impact. As I said, in most cases, I have RS smaller than R pi. This is the case. So that my RO prompt will simply be GM RO RS. Okay? So your overall output resistance will then become GM RO RS in parallel GM RC. Sorry, RC. The loading resistance. That will then give you the overall output resistance. Okay? Yes? Yes. If it's infinite, it will go back to RC because there will be ideal current source. Ideal current source will give you infinite resistance. Though you only see RL prime will be infinite if we don't consider RL. Anytime you want to consider the bridging between these two, then early effect needs to come in order for this to come in to your equation. Okay? R0是什么？哦，我写错了。It's fine. I should say sorry. 我们是 consider it is finite, so you need to consider the effect of RR. So there's actually derivation. The problem with a common base or common base structure is that it will depend on various conditions, and then your input-output resistance. This is a particular case where this is the simplest. You're assuming all the impact on the terminals are ignored, meaning that there's no base resistance, source resistance, and early effect. If all of them is included, then it will become much more complicated. But we actually don't have time to go into the derivation itself, but I'm just going to give you some of the variation effect on input and output resistance when there's other consideration in your circuit. So let me write down the key problems. One is that, what if I have base resistance? So let's look at base resistance in Rn. So I'm not going to derive it. You can actually do the exercise on your own. Or there's exercise in the textbook. What I meant by this is that if my base, assuming my base is connected to a voltage source. So voltage source will actually have source resistance or resistance of 0. So what if my base is connecting to a wire, so there might be parasitic base resistance? Let's say if my circuit looks something more like this. This was still considered as a common base structure, but there's a base resistance RB. So in a small signal sense, it will then become something like this. This will be my AC ground. So this will then somewhat impact my input resistance because there is a base resistance. So if this is being considered, then your Rn, I'm just going to give you the results, will be 1 over Gm plus this is in contrast to if, remember, if we go back to this, emitter resistance, effect of emitter resistance if I'm looking in from here. If I'm looking in from here, Rn, remember Rn will be R pi plus 1 plus beta Re. Okay? You can actually do the exercise at home. Follow the small signal equivalent circuit analogy. But this is just to tell you that if you're looking in from here, the modulation effect will be attenuated because your voltage, the current on the base will be 1 plus beta times smaller. Therefore, the equivalent resistance you're looking in from emitter will actually be attenuated by the current ratio. This is the same thing. Re will be amplified by a factor of 1 plus beta. This will be reduced by a factor of 1 plus beta. Okay, so this is one of the things I want to mention. I believe there's exercise or examples in the textbook you can go through and just get a sense as to how the resistance changes if you're looking in from emitter or looking in from base. The other thing I want to talk about before we do a small summary is the problem of having finite output resistance. This is also an example. I don't think I will have time to go through the small signal analysis. You might need to go through it on your own at home as well. But just to give you the result as to what the impact is. So remember, when we look at this 1 over GM analogy, this is based on the fact that I'm ignoring output resistance. So this is the most, I think, first principle results, meaning that, once again, this is assuming that R out is infinite. So what if R out is not infinite? What is the impact? What does it impact, and especially input resistance? How does it impact the input resistance? So the way to do this is that you could actually do the more complicated structure. I'm just going to write down how you do the exercise on your own. So this will be my equivalent circuit when I include R out in the equation. And this will then be my V pi, R pi. And common base, therefore this is ground. So the testing condition will be given a test voltage and looking at test current. This is when RO is, let me make sure, it's finite. It's no longer infinite. Okay? So what you do is that you find out what is the Rin, defined as Vx, Ix. The problem is that you would then have additional current coming in from here. This will then lead to certain complication. But let me just give you the results. You just do the same exercise, you should get the results. So this will then become 1 over GM plus. So the impact of RC will then coming through because of this feedback thing through this through the R out. So then this will then give me something. Just going to give the results. So what does this imply? One of the key things is that if I'm having, in most cases, if my RC is much, much smaller than RO. If this is the case, you will still have Rin. This approximation still holds. Right? If I'm writing this down, this is, if I'm rewriting this equation, it's 1 over GM, 1 plus RC RO. As long as my RC is smaller than output resistance, as long as this holds, this will still be relatively true. This approximation will still hold. One of the problems is that when does this become a problem? Let me ask a question. So if this is the case, let's say if I have an ideal current source as my bias. This is more conceptually. It's not necessary. It will never be realized because you won't have an ideal current source. But let's say if I ask you this question, if, example, if ICQ is ideal, what should your input resistance be if this is the case? What do you think? Ideal ICQ will give you what? This effective loading resistance. What is Rn? If I'm following this equation, what do you think? If I ask you this type of question, there's only two answers. One is 0, one is infinite. Okay, you're right, it's infinite. If this is ideal, this means that this, if you're looking in from here, this is the resistance, effective resistance from the load is, I should say, R load. Let's say this is R load. It's infinite. Therefore, infinite divided by a finite number should give you an infinite result. Okay? So this is something that you need to, of course, this is conceptually true, but if I ask you in terms of concept, it will then passing through. So if this is the case, what I'm trying to say is that even though in common practice we assume a common base stage will give you low input resistance, but not necessarily true if this happens. So you have to make sure that your environments actually ensure that you still have 1 over GM. It's not necessarily always 1 over GM when you need to consider the loading effect, your loading resistance effect. So before I before we go to the break, I would like to just give a small little table. Let's just generate a table before we go. So there's also two conditions. One is we consider two effects. Let me try to construct the table again. So we're only looking at 3 parameters as well. 1, 2, 3. Looking at this is common base stage. And this is the situation we consider. First, we're assuming R out is infinite and no effect of RS. There's no source resistance effect. That's the most basic. We look for gain, R in, R out. So based on our finding on the first analysis, this is GMRC. Once again, it's non-inverting. There's no minus sign. So input resistance approximately 1 over GM. I'm just going to give it an approximate number. And this is RC, basing on the results. So for more sophisticated consideration, if I'm assuming RO is included, and when RS is not equal to 0, then you would then have the impact, even though there's effect of RO, but it's negligible. Mostly RS will have more significant impact. So even though in the analysis that I used, I didn't include RS in this analysis, but it made very little difference. So you still get a major impact coming from source resistance. And then this will be, to be more precise. And then my output resistance coming in from top will be, I'm just going to use GM RS in parallel. Okay? Didn't get right. Hopefully. So we're assuming that most cases is when RS is very small. So I'm going to use that as an analogy. Okay? So this is a common collector stage. It looks something like this. I have an input coming in, and then input is still coming in the base, but rather than having my output at the collector, I'm taking out the output at the emitter. So what is the purpose of having a common emitter stage? If we're dealing with voltage, this is a very good, we call it a voltage buffer. For a common base stage we use in the previous stage, if by having a current gain of 1, this can be often used as a current buffer. But what if you want to buffer voltage? It's a voltage buffer, or sometimes referred to as a driving stage. I will explain that in just a little. These are just the naming of this particular architecture. So what is a voltage buffer? If you think about it, it's basically a voltage amplifier with a current gain of 1. So an ideal voltage buffer will look something like this. R in, R out, V1. So whatever you take in, you simply deliver it out. So for an ideal buffer, a voltage buffer, you basically want input resistance to be what? If I'm taking in voltage, what do I want? Once again, this is your VL. Okay? So what do I want for input? So that it will be independent of RS and R load. What do I want for input? High or low? Just a pick. High or low? What do I want for voltage buffer? Voltage amplifier, the same as a voltage amplifier, just a gain of 1. So I want high. I want infinite. And I have a voltage gain buffer. I have voltage gain close to 1 because it follows. And then I want an output resistance close to 0. Right? So if this is infinite, this is infinite, this will be open circuit. It will take in whatever V in. If this is open, V in, V1 will equals to V in. And if this is 0, V out will equal to V in. That's what you want for a buffer. Voltage buffer is truthfully 100% deliver whatever is being taken in. That's what a common collector stage wishes to deliver. To provide, it's not to provide high gain, it's to provide close to 1 gain. And to be independent, to be less dependent on this. You want your output to be, once again, independent or less sensitive, not necessarily less sensitive. I should say less sensitive to the environment. Environment are RC or loads. I want to make sure that it doesn't matter what my source is imperfect is or how much I need to drive the output, meaning that the loading resistance is very, very small, I will still be able to deliver whatever voltage is being taken in. So ideally, this will be 0. R out. As I said, RL equals to 0 will be short. And Rn equals to infinite will be open. That will give you an ideal voltage buffer. Right? What's your song? R out. Oh, yes, correct. I'm saying 0 but writing down infinite. Correct. Okay? So let's see how does a common collector stage deliver this. So we still need to generate my small signal model. Equivalent circuit. So the first thing we do is to generate a small signal equivalent circuit. The same thing, we're assuming output infinite, source resistance equals to 0. We're ignoring that at the beginning. So this will be my input V in and model, small signal model, R pi, V pi. This will be GM V pi. And I'm also ignoring the output resistance. You can include that. It's not that complicated, but just to make our life easier. Let's ignore it at the beginning, just to get a sense as, oh, I'm actually including, but never mind. So let's include R out. So if I'm including R out, it will look something like this. I could actually include that without too much pain, then you just include it so that it will be more complete. Okay? So where's my, let me highlight the input and output terminal. I have input coming in from the base, output at the emitter. So this is my input terminal here, and this will be my output terminal. So we start by writing down what Vout should be. Vout will be the current. If you're looking at this terminal, I could simply flip this downwards so that it will be easier. So I could flip this R out down. Instead of connected to the collector, this is ground, this is also ground. So you could flip it, it will be the same. So that if you're looking at this terminal, the current coming in will be, the current going out will be R out divided by R in parallel RO. This is the current going downwards. Equals the current coming, equals to GM V pi plus V pi R pi. Okay? So this will be the I should say KCL at terminal emitter terminal, at the emitter terminal. And node E, right? Current coming down from this two branch equals to current going down. And then the other thing is that if you're looking at this branch, this will then give us that V pi plus VL equals to Vn. Right? This is my Vn equals to V pi plus VL. This is VL. Let me highlight again. This is VL. It's the same terminal. The emitter is my output terminal. So Vin equals to V pi plus VL. Did I make this? Okay, good. Let's make sure that I didn't get. Okay. So using these two equations, I could actually summarize it to get the output and input relationship. So you can do some rearrangement to make it make V pi as a function of Vn. And then we could get the ultimate results. It will be Gm Re in parallel Ro. 1 plus Gm Re in parallel. Okay? So in most cases, as I said, the emitter resistance is typically fairly small. In this type of design, in most cases, your RE will be much, much smaller than R0. Therefore, the voltage gain will then be GMRE 1 plus GMRE. Okay? And by design, if we want to deliver a close to voltage buffer, ideal voltage buffer, the second thing we do in most cases, in most design, I should say in most design, the design purpose is to deliver a voltage buffer. Therefore, you want the gain to be close to 1. So how does one do that? Because GM is something that we can design. So in most cases, we want to design 1 over GM to be much, much smaller than RE. Or you could say that GM. So what does this simply implies that you make GMRE larger than 1. Even though I say larger, in circuits perspective, larger meaning typically 10 times will be larger. That will give you almost 0.9 in your voltage gain. So your voltage gain will then become approximately 1. that will give this will then deliver a voltage buffer. Well, you simply not to amplify. You want it to be, once again, if you go back to the name, you want it to be a follower. What does it mean by a follower? Meaning that if I do this, you do this. You do the same thing. As long as you follow me, then follow, especially 100%. If I give you a gain of 1, meaning that it follows to 100%. Okay? But in most cases, if you're doing a design, it's typically 0.8 to 0.9. That's a typical number. Okay? So we could, I don't know, we still might have time to look at input resistance. So input resistance will be something like this. So the equivalent circuit will be something like this, GMV pi, R pi. And I'm giving a test voltage looking at the test current. Give me a second. Fix this. Okay. And this is the equivalent circuit we're using. Should be able to obtain the input resistance. We can actually do the exercise, but let me just write down. The Vx will be V pi. This is V pi. Plus the output resistance will be Ix. This will be the current coming down. Ix plus GMV pi. That will be the overall current going down to this network. RO in parallel RE. Okay? And then we know that this, you want to write down V pi as Ix, because there's only one branch. V pi, Ix is actually the base current. So Ix R pi. We substitute this into here and here. And then we can get the results of Vx as a function of R in, by definition, is Vx Ix. Then the results will be, not surprising, it's the same as what we did in our previous analogy, which is this resistance plus whatever is being amplified at the terminal. I should include, to be more precise, let me rewrite it. Will be R pi 1 plus beta RE in parallel R. Well, you can typically ignore RO because RO is much, much smaller than RE in most cases. Okay? So then we see that it has relatively high input resistance because R pi is typically a much higher number than 1 over GM. Therefore, it's beta time higher. So it's relatively high input resistance. And its output resistance is coming in from here by shorting input. So you're actually seeing these, mostly these two. So I don't think we have time for that because people are coming in for quizzes. So let's stop right here, and then we could resume our discussion on the final analysis on common emitter next. So let's stop for quiz.